Assalamu alaikum and adab, dear students. In this lecture, we will study the analysis and design of a strut. The strut is a compression member. This is also designed as a compression member, just like a column, but this is the member of a steel roof truss. A steel roof truss, we analyze the steel roof truss for various forces acting on it, which is distributed among the nodes of that particular truss. And when we analyze the members, certain members, we find that they carry axial compression, and while as other members carry axial tension in it. So the members which are carrying axial compression, these are designed as struts, while as those carrying axial tension are designed as the tie members. So this topic will be covering for this such like members which are carrying axial compression in a steel roof truss. Now first we see the structurals. The common type of structurals used as a strut, these include maybe a single angle section which is connected to the gusset plate, maybe equal or unequal as the case may be. This is a single angle section used as a strut. We may use a double angle section which may be connected to the same side of the gusset plate like this, or it may be connected to either side of the gusset plate. So this will appear like this. So these are used as common sorts of structurals as struts in a steel roof truss, or where the roads are heavier, we may use a T section even. We may use a T section to act as a steel roof, as a strut connected to the gusset plate. These are common sort of types of structure. We may use some heavier sections if the loads are too heavy. Then we have effective length of the strut, small l denoted by small l. Total length of the member, that is the length from center to center of intersection is the total length of the strut, and we have to find out the effective length. Now this depends upon various factors: the type of strut, the members used in it, the end connections which we are providing. Say these struts are classified into continuous struts, or they may be a discontinuous member. So depending upon their continuity, whether they are continuous or discontinuous, we determine the effective length of that particular member as per the IS code provision. So IS code has given various provisions for effective length as well as the permissible axial stress to be taken for the particular cases. So it depends upon case to case. For example, if the member is a continuous member, according to IS code, the effective length for that continuous member will range from 0.7 to 1 L. This will be the effective length. Sigma AC, that is the permissible stress in the strut in axial compression, shall be taken directly from the table, that is IS code table 5.1. This is the provision in case the member, if the strut is a continuous one. Now if it is a discontinuous member, then there are many cases. If it is discontinuous, if the strut is a discontinuous one, then various provisions are there depending upon the combination of the members used as strut. Say for example, we have various subtypes in it. Say we have a single angle section. Say we have single angle connected to the gusset plate, and provision is that it is connected with one rivet only. It is connected with a single rivet at each end. Or it may be a single angle section connected with two or more rivets, or a fillet weld. So this is the case as in discontinuous type of member. Then if it is a single angle which is connected at the ends by a single rivet only, effective span or effective length is taken equal to the total length of the member, that is center to center distance between the intersections. And here sigma AC is to be reduced. It is to be taken 80% of sigma AC from table. Okay, so sigma AC is 80%, 0.8 times the value that we obtained from the table. If it is connected, the same member, single angle section, but this time it is connected with more than two rivets or a fillet weld, then L is 0.85 times the center to center distance between the intersections, and sigma AC is to be taken full sigma AC from the table. So these conditions are provided in IS code, what effective length of the member we have to take, and sigma AC whether it is to be taken full from the table or it is to be modified. Similarly, there are other conditions also. This was for the single angle only. In discontinuous members, there are double cases for double angle also. If it is double angle section connected on both sides of the gusset plate, the conditions are given what effective length and what sigma AC we have to take. If it is a double angle section again, and this time connected to the same side of gusset plate, then provision of the rivets, 2 or more rivets or fillet weld. So these conditions are provided in IS code. For each condition, what L we have to take and whether sigma AC is to be taken directly from the table or if it is to be reduced. So we will be referring that table in IS 800 for calculating sigma AC and for the effective length of this strut. Then we have slenderness ratio. Slenderness ratio of the strut. It is represented by lambda, and slenderness ratio is L divided by R minimum. Minimum radius of gyration. Now L we have obtained, radius of gyration. This will be, if it is an angle section, if it is a single angle section, we can get R from the steel table directly. Say if it is RXX, we will have RYY also for an angle section. We will have R about UU axis, we will have R about VV axis. So we will have 4 values of the R directly from the steel table if it is an angle section, and we will take the minimum of all the 4 values. We will take minimum as R minimum. Then we will find out slenderness ratio. But if this was a single angle section, if there is a double angle section, say we have double angle section like this, and we have to determine the least radius of gyration for this, we can even refer to steel table. In steel table, provision for 2 angles, that is a double angle, is also given. So we will find out area directly from the steel table, and if R is to be seen, R minimum, that is minimum of all the values, we will find out RXX for this case directly from the steel table. For RYY, we will have to see the value corresponding to back-to-back distance. In steel table, RYY, various values for a double angle section are given, but that is corresponding to the back-to-back distance between the angle sections. Now, if these angles are connected to the same side of gusset plate, then they must be connected to each other here, and back-to-back distance is 0. So in steel table, we will find out R minimum or RYY corresponding to 0 back-to-back distance when it is on the same side of the gusset plate. Now if it is on either side of the gusset plate will be somewhere here, and RYY will be governed by the thickness of gusset plate. Thickness of the gusset plate, that will be the back-to-back distance between the 2 angle sections, and corresponding to that distance we'll find out RYY. RXX is known to us. We'll find out the minimum radius of gyration, and then lambda, that is the slenderness ratio corresponding to this value of L and R minimum. Then we come to the load carrying capacity. Load carrying capacity of a strut. So how much load this strut can carry? First of all, we have to see the data given. Given data shall include the section. The section details shall be provided, whether it is a single angle, whether it is a double angle, if it is connected on the same side or on the either side of the section, the overall length of the member, end connection, details of the end connection, whether it is connected by a single rivet at the end, whether it's connected by two or more than two rivets, whether it's connected by a fillet weld. This data is required to find out the L and the modification to sigma AC if required. This is needed, and we should know the yield stress of the steel, structural steel, for this particular load carrying capacity calculations. Then, after we know the sectional details, we go to the steel table. From steel table, we find out the area. If it is a single angle section, we will go to the single angle section and find out the area of the member. If it is a double angle section, even then the data is available in steel table. We can go to the double angle section and then find out the area of both the angle sections together. Then we'll find out R minimum corresponding to our XX or YY or even UU, and VV will find out the minimum radius of variation. We'll see for this particular case, the section is given what L we have to take from the steel table, from the IS code, and sigma AC, whether sigma AC is to be modified or taken to be as full value from the steel table. We'll find out this from IS code corresponding to the condition given as continuous member, discontinuous member, single angle, double angle, and connect corresponding to the end connections also. So we'll find out this L and sigma AC to be modified or not. Now we have area, we have L, we have R minimum. We can calculate the slenderness ratio lambda. Slenderness ratio shall be L divided by minimum radius of gyration. So this will give us lambda. Lambda in no case shall exceed 180. So for a strut, lambda has to be limited to value 180 or less than that. It should not exceed 180. After we calculate this lambda, we can now go to the table of IS code to find out sigma AC. So corresponding to lambda, we from the IS code table number 5.1, we find out sigma AC. Sigma AC is permissible axial compressive stress. In that table, the sigma AC is varying corresponding to this with respect to lambda and Fy. So we interpolate the values. These values are given 10, 20, 30 and so on. This is given for 220, 230 and so on, 240 Fy, whatever is our value, and wherever in between two values where our value lies for lambda, we will interpolate. We will interpolate the value of sigma AC. Then we'll find out the load carrying capacity of the strut as the gross area of the member multiplied by sigma AC. Here we'll have to see whether the sigma AC is to be taken full or if it is to be reduced as per the condition given. Multiplying it with the gross area will give us the load carrying capacity of the strut. So this is member, it depends upon the member, the connectivity of the members and the end connection as well. Then we have design of a strut. If the load is given and member we have to select, then that will come under the design of that particular member. So in this, the data given, this time no section will be provided, load must be given. This time will be provided the load for which the angle strut or simply strut is to be designed. The length of the member between the intersections, that is the total length L, and condition and connection, whether riveted end connection is to be provided or welded end connection is to be provided, whether a single rivet end connection is to be provided or more than one or two rivets are to be provided. That must be given the condition. Yield stress of steel, this must be given to us. Now for these conditions, They may also specify whether we have to use a single angle section, or we may have to use a double angle section. And again, in double angle, whether they are connected on the same side or connected on either side, it may be specified. If it is not specified, then it will be our choice. It may also be specified whether equal angle sections are to be taken or unequal angle sections are to be taken. Whatever conditions are given, we will abide by those conditions, or whatever is the data missing, we will assume it suitable. Then in the second case, we will assume sigma AC initially, because we don't have this value, we need this value to determine the gross area. We'll initially assume this value between 80 to 120 Newton per mm square, just to select a trial section so that we can go on and check that trial section. Then we may go for some other revisions as well. We'll also find for this case now what is the effective length parameter. If it is single angle, whether it is to be reduced or it is to be taken full, and sigma AC for this case, whether it is to be taken directly from the table or it is a reduced value. We'll find out this condition also, which we will follow accordingly. Then we will calculate the gross area. We'll find out gross area required. So this gross area required for the member shall be the load divided by the value assumed for sigma AC. This will give us the gross area for the member required. Once we get the gross area, we will go to the steel table and we'll select a section accordingly. We will select a section which will have a gross area more than our requirements, and if it is a double angle section, we will look from the double angle sections. The area requirements shall suffice, or if it is a single angle section, then a single angle should provide us so much area required. We will also look for the R value of that particular member. Higher the R value will give us lower lambda. Lower the lambda, higher will be sigma AC, and higher will be our load carrying capacity. So from steel table, we select a trial section. Select a trial section from the steel table according to the conditions given. For this particular section, we'll find out area in millimeter square. We'll find out the value if it is x, whatever are applicable, rxx, ryy, if uu and rvv are also applicable. We'll find out all these values. We'll also see whether ryy is to be taken for a single angle, then it's directly available, or if it is to be taken corresponding to the thickness or the gap in between the connecting legs of the member. If it is the thickness of the gusset plate, then we may have to calculate it for ryy may be taken corresponding to the thickness of the gusset plate if the angles are provided on each side. If they are provided on same side, then ryy may be taken corresponding to 0 back-to-back distance. If the thickness of the gusset plate is not available, say for example, we may have a case of double angle section connected on either side of the gusset plate like this, and the thickness of the gusset plate is the back-to-back distance between the two. If this thickness is not available in the steel table, the thickness of the gusset plate is not available in the steel table, then we have to calculate by the standard procedure. Then we'll have to go to the first principle and to calculate ryy corresponding to this axis. For that, we may have to find out Iyy. Then we'll find out ryy as under root of Iyy divided by the gross area of the member. So Iyy will have to look at the thickness of the gusset plate. If it is available in the steel table, only then we can take it directly. Otherwise, we'll have to go by the basics. So we'll find out R minimum, and then we'll calculate slenderness ratio, L upon R minimum. Slenderness ratio should not exceed 180. This is the condition. If it is exceeding, we'll here revise the section here itself and take another section such that this condition is sufficed. Once we get lambda, once we get the value of lambda, we go to the table 5.1 of IS code and determine sigma AC from that corresponding to this lambda and yield stress of steel. From this lambda and the value of steel stress of steel for corresponding to these two values, we'll find out sigma AC from the table, and finally determine the strength of this particular member what we have selected. We'll find out the load carrying capacity, how much load it will carry. So load carrying capacity of this trial section will be given by the gross area of that particular member multiplied by sigma AC. Here we will have to see the sigma AC, whether it is to be taken full or if it is to be reduced as per the conditions given, as per the already notified conditions, whether we have to reduce it or not. So this will give us the load carrying capacity, and this load carrying capacity has to be more, this load has to be more than the load required for the particular strut. Only then it is safe. If it is not so, if load carrying capacity is less than the required capacity of the strut, we will have to revise the member. We will have to choose another section with corresponding heavy area, more area, and R, value of R should be higher. Correspondingly, it should be higher than the previous section what we have already selected. So this condition has to be met, that the load carrying capacity has to be more than the load which is coming on that particular strut which it has to resist. After we achieve this condition satisfactorily, we have to go for the design of end condition and connection. Design of end connection. Now, if end connection is defined, if it is a riveted end connection, we'll go it accordingly. If it is a welded end connection, then we'll have to provide a fillet weld. So in end condition, we'll find out the rivet value corresponding to its shear strength and bearing strength. Then we will find out n number of rivets, that is the load divided by rivet value. We'll find out the number of rivets, and then we'll find out the spacing where these rivets shall be placed. We'll find out how many rivets we are providing. Depending upon how many members we are connecting, we'll provide the rivets accordingly, the number of rivets, their center to center distance pitch, their edge distance, and the lap distance, overlap. If it is a welded end connection, then we may have to go for the weld length to be provided. Then we'll have to provide the length of the weld. We'll find out the length of the weld required and accordingly provide this fillet weld, so that the load carrying capacity of the entire welded connection is same as the load carrying capacity of the strut, and the CG of the connection, whether it is a riveted end connection or a welded end connection, that CG should match with the CG of the member, so that there is no eccentricity. So in a strut, we conclude that which is summarized, that in a strut we will have to see whether the member is a continuous member or a discontinuous member. If it is a discontinuous member, we have to see whether it comprises of a single angle with single rivet at the end, or more than two rivets at end connection plus a fillet weld, maybe a fillet weld also. Then we will have to see whether it is a discontinuous member with two angle sections connected to same side or both sides of the gusset plate. So all these factors we will have to see. Accordingly, we will have to refer IS code and find out the effective length values, what effective length we have to take, what sigma AC value we have to take, whether we have to reduce it or not. These conditions have to be first of all seen, what we have to follow as per the condition given. Then we will have to find out lambda. Lambda will be the slenderness ratio. This will depend upon L and R minimum. R minimum we can take from steel table. Again, if it is a double angle section, then we'll have to see R XX we can take directly. RYY we will have to see corresponding to the back-to-back distance. If it is on the same side of the gusset plate, then back-to-back distance will be 0. If it is on either side of the gusset plate, then thickness of the gusset plate will be the back-to-back distance. We'll find out lambda. We'll go to the steel IS code table for finding out the sigma AC value, and load area multiplied by this value of sigma AC shall give us the load carrying capacity. In design, we'll initially assume a value of sigma AC We'll find out gross area required. We'll select a section. We'll determine the load carrying capacity of the section. If it is satisfying the conditions, then it's okay. If not, we'll revise the section and then design the end connection as well. Thank you.